So when you're looking at data in a table, at some point you probably looked at a database and found some dodgy information, such as lots of duplicate rows, things that should not have two copies of in a table, but actually there are multiple of them. Or maybe there are some impossible values. So let's say you're calculating percentage correct for exam, and the values should be between 0 and 100, and you've got negative values or values way over 100. It's like we've got impossible values there. Or probably the most common one is missing information, or what generally we mean in database terms is there's null values when you expect there to be one, right? And it's fairly, can be sadly quite common to encounter these kinds of problems in your database. And they fundamentally come from a lack of having database constraints. And if you create the constraints on your table, it prevents certain types of data errors. The database will detect them as you try and insert and update your data, making these kind of situations impossible. And there are 5 key core constraints which we will look at today. So first up, we've got primary keys and unique constraints, which we can use to prevent duplicates values being stored in a table. There are foreign keys, which we can use to enforce a parent-child relationship. There are not null values, which you probably guess from the name, prevent you storing nulls. And there are check constraints, which allow us to check various conditions. So we'll look in these in detail in this session. So hi everyone, I'm Chris Saxon. I'm part of Gerald Venzel's app dev team in Oracle Database. I'm here to help get the best out of Oracle SQL and PL SQL, and hopefully have some fun whilst doing so. So with that in mind, as I say, we will be looking at database constraints. And we'll start off with the problem of duplicates, right? So in general, in life, it's quite useful to have some redundancy, spare copies of things. For example, it's generally a good idea to have a spare copy of the keys to your house or your car and things like that, just in case one goes missing. But in database terms, generally, you do not want 2 copies of a row, 2 rows to be identical or have duplicate values for columns that are supposed to be unique. So, and when that happens, it becomes hard to determine what you're looking for, and there can be mismatches and all sorts of problems. So the question is, how do we stop this? How do we stop you having duplicate values in a table for a particular column or set of columns? And as I said, there's 2 constraints we can use for this, and we'll start off by talking about primary keys. So to define a primary key, the basic way is nice and simple. You just have your column, and we see at the end, we've got our inline constraint saying it is a primary key. So what this means is, having marked it as a primary key, we can store at most 1 row per value in student ID. So if we insert student ID equals 1 into the table, and a row has that, if another session or someone else tries to insert student ID equals 1 as well, it will fail. We cannot have 2 rows with exactly the same value for the student ID, only 1 row. So the primary key prevents duplicates here. And like I say, it's super easy to actually just create this. We'll just define it in line here. So we can do that for the student ID, and we can prevent duplicates there. But if you think about it, the other column I've got here, the email address, that should probably be unique too, right? We should probably not allow 2 students to share an email address, because that might be their login for access their accounts and that kind of thing. So we'd like to be able to prevent that too. So what happens if we try and declare that as a primary key? So we've got primary key on student ID. What happens if we try and make the email address a primary key as well? Well, we can do that with an alt table. So we can define these when creating the table, or we can add them after the fact with alt table, and we've got our primary key here. And you see I've marked it in red. Why have I marked it in red? Well, it's going to fail. It's going to fall over in a big heap, because a table can only have 1 primary key. You can never have 2 or more primary keys on a table. So if that's the case, how do we make sure that the email addresses are unique as well? We made sure that the student IDs are unique. How do we do the same for the email addresses? Well, I've said the word unique a lot here, and I'll probably say it a lot more in this session as we continue. The solution is add a unique constraint on it. So what we could do actually, rather than making student ID a primary key, we can actually make both of these columns unique. So you can see I've got the unique keyword after each of them. What this does is it creates separate unique constraints on each of them. So that's not one unique constraint across the combination of them. It says we've got two different unique constraints, one on student ID and one on email address. So they must individually be unique, those columns. You can create multi-column primary keys and unique constraints. We'll see an example of that later on, but if you do it inline like this, they are separate constraints. So it's just on that individual column. So this kind of highlights the first of a few differences between primary keys and unique constraints, namely that you can only ever have one primary key, but you can have many unique constraints on a table. So to show further the differences between these and see them in action a bit more, let's jump over to a little demo. I'll start off. So we had our students table, and you say we were recording our student and ID. I'll make that the primary key. Now notice here, I'm actually naming the constraint. You don't have to do this, but I would strongly recommend you do this because it, we can then use this information. It's in the data dictionary. It's easier to identify what this constraint is if we give it a meaningful name. If we don't, as we'll see in a second, the database it'll make up a name for it, which is not quite so obvious what it is. So we've got a primary key on student ID, and we made email address a unique constraint as well. So we've got our two constraints. Now this registration number, I haven't actually made any kind of constraints on it at the moment, but what we want to do, let's say that this is actually a unique identifier as well. This is some code students are given either to initialize their accounts or access them or something. So in fact, all three of these columns are things that we want to apply unique constraints on. So let's just create the table to start with. We've got it. So we need to add a unique constraint or enforce uniqueness on the registration number. Now, just to kind of prove the point, table can only have one primary key. We've got a primary key, and so if I try and add it, we get a big error. The whole thing falls over in a big heap. But I can add another unique constraint. So even though we've declared email address as unique, we can make registration number unique as well. So there we go. That we've now added that constraint to the table too. And we can see it by looking in user constraints. So constraint type P for primary, U for unique. And you can see there's our named constraints. And notice I didn't actually give the registration constraint a name. So we've got this lovely sysc something or the other going on here. So as I said, while you don't have to name these constraints, I think it's a very good idea too, because it just makes it much clearer when you're looking at the data dictionary what's going on. And it can also be useful for things for like error handling and so on. So we've got our primary and unique constraints, and let's just put an initial row in the table. We'll save it. So at this point, we've actually got separate unique or primary constraints on all the columns individually. So we can't add another student ID 1, another first.id email address, or ABC123. Just kind of prove that. We'll try and put these all in, and all of these will error. Okay, and we get the name of the constraint that actually caused the problem. So student ID, email, and sys, blah, 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 whatever the heck that actually means, right? Good idea to name your constraints. So they're all individually unique. So at this point, there's still primary and unique constraints look very similar still, right? The only difference so far appears to be we can add many unique constraints. However, there is another difference when it comes to handling null values. So let's try and insert null for the columns. And we put these in and just try and run this here. You'll notice we cannot insert null into the primary key columns. So always, primary key columns are always mandatory. You can never add null to them. However, our unique columns, we can insert null into them. So we can see we've actually got 2 rows for each of them, which are null. So another thing is Oracle database does not consider null values to be equal when it comes to enforcing unique constraints, right? So we can have as many rows as we want, which are null, where all the entries in a unique constraint are null, okay? So another difference here is you can never have nulls in a primary key, but you can in a unique constraint. Okay, so we've added our information here. And one thing to note here is, however, we've got our email address in lowercase. What happens if we add it in uppercase? Or actually we change the registration from upper to lower. So the characters here are the same, it's just the case is different. So by default, these are case insensitive. And this might not be what you want, right? You might want to enforce that actually it doesn't matter whether they're upper or lowercase. We just want the letters to be considered unique, regardless of case. So it's an interesting question here is, how do we do this? How do we make sure that it is unique case insensitively, right? And just kind of prove the things. This collate clause added in 12.2 means we are going to use changes to searching and sorting semantics. So collate binary CI, binary case insensitive. So we're doing case insensitive comparisons of the email address and registration number. So that means when we group by them, values, the same letters will collate together, even if they are in different case. And we run that, we can see we've got 2 rows for these, and again, 2 rows for the nulls as well. So what do we want to prevent this? What do we want to stop this happening? Well, first up, let's just remove the duplicate to make things so we can actually add the constraints later, and remove the unique constraint. So I can name the constraint specifically, say drop constraint, or I can just say unique and the column it is on, right? So I'm removing the unique constraint on email address. I don't actually need to know what it's called. So we can remove it in that way. Now, one way we might want to try and do it is just try and add the new unique constraint, but like a function-based unique constraint. Unfortunately, this ain't going to work, okay? The database doesn't let you do this. Primary keys and unique constraints can only be on identifiers, on columns. You cannot have expressions here. So is all hope lost? Are we unable to make this case insensitive, unique case insensitive constraints? Well, no, we can actually create a function-based unique index. So we can put the collate clause. So do the comparisons case insensitively, case insensitive comparison, and we're going to make our unique index. And we'll just create that, and let's just look at the indexes on the table. And you can see there's the function-based index I've got. And you can see it's got this sys thing. It's actually, what's happened under the hood is the database has created a virtual column for us on this NLS thing, which is what the collation does for the case insensitive comparison. So now the database is enforcing that those are unique according to this expression. The other interesting thing to notice here is we've also got unique indexes for the primary key and other unique constraint on registration number. The database uses indexes to police these constraints, which obviously makes sense if you think about it. To check if a value already exists in a table, we want to just search an index rather than full scan the table, right? So it uses an index, and if there is not a candidate index already available, by default, it will create a unique index for us, okay? So the database has created a unique index on those columns, and we've got our function-based unique index. So now we've got case insensitive unique indexes. That's right. And notice actually, even though it's a unique index rather than a unique constraint, we still get the same error, error1, right? And they all ultimately give the same error in the end when we try and insert a duplicate. So this is nice, but what if we actually really want a unique constraint? We want to make the primary key case insensitive uniqueness on the primary key. And let's drop the index. So we could do the function-based index, but we can actually do this using just regular constraints as well. But in order to do that, we will make the column case insensitive. By changing the column here and adding the collation clause, what I'm doing is saying, make this column case insensitive, use case insensitive comparison rules. So we'll do that, it adds it, and now we can add the unique constraint on the email address. So we'll create that, and now again we have now prevented unique duplicate values case insensitively. It's pretty neat, right? So what's actually going on under the hood here? I'll just pin this to show what's happening. It's actually really doing the same thing as what we had before. We can see, okay, it's slightly changed what the data default is in terms of what it's exposing, but it's basically doing the same thing. When we add the unique constraint on our case insensitive column, then the database creates a virtual column for us and then indexes that, which is basically how function-based indexes work. So the key thing here is if you want to have a kind of function-based primary or unique constraint, you can do it by creating a virtual column and then placing the constraint on the virtual column rather than trying to put the expression in the constraint itself, which can't happen. Okay. All right. So we've got our indexes here. And as I said, the database created these for us automatically. So what happens if we drop the constraint? Well, just like it created the index, it's also going to remove the index by default. And it's possible you don't want that to happen, right? You probably, in some cases, we might want to remove the primary key or unique constraint, but preserve the index. So we can have this keep index. So we can do it when dropping the primary key. We can also do it when dropping the unique constraint. So we'll remove the primary key and notice when we just dropped the unique constraint, we've no longer got, you know, a unique index on registration number, but we still got the function, the unique index, the index on student ID. Okay, so if you want to remove a unique or primary key constraint but keep the index, use the keep index clause. When we want to re-add the primary key constraint, so let's just add it back again, you might want to specify which index to use. So like I said, the database by default will create one. In this case, we don't have to do this. The index already exists. It will pick it up. But if we want to be explicit and say, maybe there's a choice of indexes to choose from, or we want to set the index properties while doing it, we can specify when using index when adding the constraint. We'll see later on a reason why you may want to do this. So that's kind of like the initial demo. Any questions or comments on that before we move on? I see there's a question came in a little while ago about temporal validity. So is period temporal validity considered as a constraint? So for those of you who don't know, temporal validity, if I just kind of create a table, let me just do create table, C1 date, C2 date for P, there we go. And I need to drop my table because I've done it. No. There we go. So we can create that. I'll come back to this right towards the end because I think we're kind of jumping ahead in terms of the types of constraints we're looking at here. Okay, if the duplicates already exist in the column, can you still add the constraint? Yeah, you're preempting where I'm going to go. Keep that question in mind. We'll come to that towards the end. Okay, and then I see this thing. Boom, boom, boom. Okay, given this compound index, create unique index. Hang on. Let's just, somebody's put some code in. So let's just see here. We've got with that. Okay, so what's going on here? Let me check. So we're creating a unique index on our table and we can insert a whole bunch of nulls. Yep, they're fine because we don't allow duplicates. We can then insert these because, oh, into my table, sorry. Let's just rename, let's do, helps if I actually fix it, doesn't it? So it does what it's supposed to do. So they can all go in. They all went in, didn't they? Yep, they all worked. Check they actually work right before diving ahead. So those all go in. Yep, okay, that's fine because it's the combination of C1 and C2 that are not unique, but this is not allowed. Yes, yeah, because the value 3 already exists. Okay, so we have a duplicate for this here. It's only if the whole entry is null, right? Either all the columns have to be null or to allow these duplicates. If it's partially null like this, it will check the other values, right? So we don't have kind of partial uniqueness here. You've already got the value 3 inserted, so we cannot insert another 3 something, okay, whatever that something happens to be. Could be null, could be some other value, okay? So, all right, hopefully that answers the question there. When you drop a PK constraint, depending on the constraint created the index or the constraint used an existing index, the index may not be dropped. How to identify what method was used and to ensure the index is always dropped. So yes, so as I said, we can use this using index, and the database, if there is an existing index, database can pick one up automatically without having to create one. There, you can also specify drop index, I hope. Let's give this a try. There you go, because it's dropped the index as well. If you want to be absolutely certain, specify keep or drop, be explicit, right? To know exactly what's going to happen. And that index doesn't exist. Let me just remove that, just add the constraint back because I'll need it. I'm not sure how you can tell exactly whether it was an existing one or not. You could kind of infer it by looking at creation dates, maybe, of the constraint and the index, but the answer of how do you ensure whether it's always dropped or always kept, use the explicit clause, and that will do what you say, okay, if you're not sure or want it to behave a particular way. But 3 already existed with 1 and 2 as well. Okay, but hang on. No. Okay, yeah. So 3, there is no row 3-1. So 3-1 is unique. 3-2 is unique. 3 null is unique. 3 null is then not unique because there is another row with 3 null, right? Right, there is no other row 3-1. If I try and add 3-1 again, that's a duplicate, right? I'm struggling to see what you're struggling with. There is already another row where one of the columns is not null that has the values you're inserting. So if you've got a multi-column primary unique key, if one of the columns is not null, even if the others are, then if the rest of the values match, null or not, then it will you'll get the OR1, right? Okay. These are allowed in because they are different values. They do not exist in the table currently. But now I've actually inserted them, you'll see they now error. So it's only when all the columns are null that you allow duplicates, okay? I mean, I hope that answered what you were looking for, Joseph, with these nulls, but basically, you know, you can see these, like this is a duplicate of that, and that's the columns of the unique constraint or the primary key, whichever it was, unique index, okay? So we can't add it again, okay? But we can add null however we want, right? Null. But if I can't add null 1, right? Oh, no, yes, no, I can add null 1, but yeah, there we go. So there you go. See, just seems inconsistent that multiple null are allowed when multiple 3 are not. Them's the rules. That's the way it works. I mean, why does it behave that way? That's just what was decided, I guess, right? You know, some things you just have to accept. That's what it is. Okay, you know. I will be talking a lot more about nulls in a bit, so just keep this in mind, right? Okay, then. So let's move on. So just kind of recap. As we saw, we can use primary keys to prevent duplicates, but there is a maximum of 1 per table, and you can never store null values in the columns of a primary key. Unique constraints, you can have as many as you want, and you can store null values in them. Now, both of these, when you create them, the database will use an index to police them, to check whether there are duplicate values. By default, it will create a unique index for you. You can override this manually, and you can create unique indexes yourself as well, should you wish to. That can be useful, necessary, if you want function-based unique constraints. Well, as we said, you can emulate that with virtual columns and so on. Okay, so at this point, you can see we've got primary unique keys and unique indexes. So some of you might be, well, why bother with primary keys? Why don't we just use unique constraints for everything? After all, they do the same job, but primary keys have more restrictions on them, right? Why don't we just make everything unique constraints? Well, why do we even bother with unique constraints? Why don't we just make everything a unique index, right? So keep this question in mind, and we will move on to discuss the next thing, and that is parent-child relationships. So we started with our student table. Let's say we also want to record which courses they are taking. So there's going to be a big list of their courses. So one-to-many relationship, parent-child relationship. The key thing here is we want to ensure every student ID we record in this student table, student course table, has a matching parent student. There shouldn't be non-existent rows. We shouldn't have people registered to courses where we don't actually record what their student details are. That should be impossible. If we write a query like this should always return 0. So the question is, how do we stop this? How do we prevent this? How do we prevent orphaned values, right? How can we stop this? Well, the answer is foreign keys, and this defines our parent-child relationship. So foreign key goes on the child table and it points to column or columns of the parent table. So we can do something like this. We've got our student courses table, and I've got 2 foreign keys, one on the student ID to the students table, and another, I haven't shown it yet, but imagine we'll have a courses table as well, right? We don't want people registering on courses that we don't know what the course is, okay? So we'd also have a courses table. So we name the constraints, and the references says it's a foreign key to students, which is the parent table. And that means every student ID then has to match a value in the students column. So the question is, what is it matching, right? I haven't listed columns out here, what it points to in the students or the courses table. You can do this, and if you do this, it will default to the primary key, okay? In fact, it has to be the primary key that it points to. So this is kind of perhaps a clue of we might want to use primary keys as opposed to unique constraints, is we can do this shorthand, but that's kind of not really the answer, because foreign keys can also point to unique constraints as well, but we do have to tell it what it's pointing to. So we can default that, and we've got the courses table, and this foreign key points to the primary key of the courses table, ensuring there's a match there. The other thing the observant among you will have noticed is I've got these columns, but I haven't specified a data type for them, right? Now, and you might be wondering, is this really possible? Does this really work? And the answer is yes, right? I know I use kind of pseudo code and so on in a lot of examples, but this is genuine valid SQL, right? You can do this in Oracle database. And what happens here is the data type for these columns is then inherited from the columns that the foreign key points to, so ensures that they are always the same. And in general, I think this is probably a good thing. I think there are, it's one of those things, in theory, you might have rows in a child table with a different data type or different constraints on them to the parent table. In practice, I don't think I've ever had to do this, right? You almost always want them to have identical data types. So same scale and precision for numbers, length for varchars, that kind of thing. And this will just pick it up automatically. So at this point, again, I'll jump back into a demo and show these in action. So first up, I'll create my courses table, which are course ID, primary unique constraints there. I'll stick some values in there, SQL and PL SQL 101 courses. And so we've got our student ID and course ID, and we've got our primary key, and it's a multi-column primary key. So it's the combination of student ID and course ID, which is unique here. So we can have many rows, as we saw in the ad hoc example I did a minute ago. There can be many rows for the same student ID as long as the course ID is different. Okay, so did I actually create this table? No, I didn't create the table. So let's create the table. And you notice I've omitted the data type. So the data type comes from the parent table. So that is a number. So now, once we've done this, we can only insert values for student ID and course ID, which have a matching value in the corresponding table. So we had student 1, course 1, and course 2. So those will go in, but there is no course 99 and student 42. So those fail. We get the foreign key validation error. And we can see we only get the rows, whereas the matching value for the student ID or the course ID in the corresponding parent table. So that was, as I said, by default, we didn't list the columns out, so it points to the primary key. And let's just reset this and recreate it. But this time, I'll list the unique, they're going to point to unique constraints. So foreign keys can also point to unique constraints. So the email address and the course code. We'll do that, and table's created. And if we look at the data types, they're now a varchar. Ooh, interesting. And we can now insert the actual email address and things like that. So it's matching on those rather than the values we had before. So we can see the email address and course code are what we're now storing. And this is something which could be quite useful, right? It could be quite useful to have the email address on student courses table, because then we don't need to join, right? You know, there's a good chance person logs in with their email address, so we know what that is. So to look up their details, we can just use their email address, save ourselves a join. So it's like, well, why don't we do this? Why don't we make foreign keys point to unique constraints? Why do we make them point to primary keys? And it's a bit of an interesting question. Well, I think one of the key things here is that email addresses, at least in general, can change, right? They're not stable in general. I mean, they tend not to change very often, but they can change. You know, a lot of people might use their work email address to log into accounts. When they change job, they need to update their email address, for example. So we might want to change this. And because we've got a foreign key from the student courses on the email address to the unique constraint in the parent table, Oracle database cannot cascade that change. So we're trying to change this person's email address. Because there is a row in student courses for this, the database will not propagate that. It won't send that update down to the child table, right? And this is not something that's supported by Oracle database. If it's something you'd like to see, then, you know, please let me know. You know, we can talk to see if that's worth adding. Personally, I think even if we eventually do add that one day, it's probably something you don't want to do, right? You know, this email address, this column, it's one column, one row in the students table, change that. But if we cascade that to all the child tables as well, who knows how many rows that's going to affect? Could be, you know, lots and lots of tables, tens of tables, hundreds, thousands, extreme cases, millions of rows that are affected. So a simple update then updates half the rows in your database and brings your application to its knees because everything's being updated, right? Even if one day we do support cascading updates for foreign keys, I would suggest that you probably don't want to do it or not have it enabled by default, right? So point here is, what's this distinction between unique constraints and primary keys? With the primary key, you are saying, this is the value we expect to never change. We are never going to update it, or we never intend to update it. Whereas the columns for unique constraints are values that we think we will change at some point, things like people's email address, right? By pointing foreign keys to the primary key, you're saying, don't update this column to prevent the cascading update issue. It's kind of form of documentation. You know, if you've got multiple columns which should be unique, multiple different columns which have different unique constraints on them, which of those should be the target for your foreign keys? So I think that's kind of the value of primary keys. It's kind of documentation, a kind of self-documenting schemas to a degree. Anyway, so let's just reset that and point it back to the primary keys. Here I've done it explicitly. Again, there it's implicit, and we'll put the value back in. And now we can update the email address because there is no longer a foreign key pointing to this column. Okay. So we've got the student courses. Let's make a child table of this. So for each course, people might sit multiple exams. Maybe they fail and have to retake, or there might be just multiple exams in that course anyway. So we're going to create a student course results for their exams, and again, a one-to-many relationship. Now notice this had a multi-column primary key, so we need a multi-column foreign key on our results table. So we've got our 1 to m. We've got our exam ID. I haven't created the exams table. Let's just imagine there should and will be exams table and a foreign key to that. I just haven't done that just to keep things a bit simpler for now. And we've got our multi-column foreign key. Notice again, I haven't actually had to specify the data types for these. And we've got our multi-column unique constraint across the student, course, and exam ID. There we go. So we'll create that. And now what this means is that we can only record results for courses that students have taken. So student 1 has taken course 1, but there is no student 99 or course 99. So the first one goes in and the second one doesn't. All right, so all good, right? We can no longer insert values into these columns which do not exist in student courses and therefore students and so on, right? Well. What about nulls? All right, let's try and put this in. What's going to happen here? What? The value went in. What? There is no student ID 99, but we allowed it to go in. So hang on, what? At this point, it's kind of like brain exploded. What's happened? We have been able to insert a orphan value, right? Even though we've got a foreign key here. And this perhaps is a little bit different to the example we were talking about with nulls with unique constraints. When you've got a partial foreign key like this, if any of the columns are null, then the others, the database does not actually have to check, doesn't check or validate that those other values exist in the parent table, right? So we can end up with these dangling values. So clearly, this is a whole big mess. So you need to be very, very careful if you've got multi-column foreign keys, okay? Any questions or comments on that? Because we'll talk a bit about what we can do to avoid this and nulls generally in a second. But any questions or comments on foreign keys and what we've covered so far? That sucks. Yes, I would say that although this is kind of not ideal, shall we say, I think it's very rare that, I mean, personally, I can't think of a time when I've run into this as an actual problem, because normally, yeah, it would be unusual. Yeah, so we're going to talk about disallowing nulls and not making this possible in a minute, right? Obviously, we don't want to allow this to be, we want to disallow this situation. So we're going to cover that in a second. And I think that's probably why most of us never really encountered it. Partly, it's, at least in my experience, it's fairly unusual to have multi-column foreign keys, mostly because people just slap a, single column surrogate key on every table, regardless of whether that's the right thing to do, which means it's not a problem, right? This only happens on multi-column foreign keys. If it's single column, it's not an issue. So 90+% of tables, this is just a non-issue anyway. And then a lot of the time, people have taken steps to avoid nulls anyway. All right then. So I'm not seeing any other questions or comments come in at the moment. So let's move on. So before we kind of move on to dealing with nulls, let's just wrap up one of the things. And so I had that question a while ago. It's like, why do we define primary keys? Why not just use unique constraints? Why not just use unique indexes? Well, first up, foreign keys have to point at a constraint. Foreign keys cannot point at a unique index alone. It has to go to a primary key or unique constraint. So we have to use a constraint to enable foreign keys. But why use primary as opposed to just lots of unique constraints? Well, like I say, it's a form of documentation to other developers. You are telling them, if you have a child, if you're going to create a child table for this parent table, the foreign key should point at the primary key, not whatever other unique constraints you may have defined on it. So we can prevent cascading update issues. So to recap on that, when you create a foreign key, by default, it'll point to the primary key if you list no columns. If you want to change that, you have to actually list out the columns explicitly. And you can omit the data type if you do it when defining the column, and it will inherit the data type of the primary key or unique constraint. When it comes to having foreign keys reference unique constraints, you need to be very careful to make sure you're not going to run into the cascading update problem, right? They say that Oracle database doesn't support this, but even if it did, it's something you probably don't want to happen anyway, okay? However, as I say, there are some situations where you might want foreign keys to point to unique constraints to enable certain types of business rules. Now, I don't have time. That's a bigger topic and a conversation for another day. If you're interested, let me know, and maybe we'll discuss that in the future. But sometimes you might want foreign keys to point to unique constraints to enable certain types of business rules, to enforce certain types of business rules. Finally, when we've got multi-column unique foreign keys, be very, very careful if any of the columns are optional. They allow nulls. So that leads us on to the final kind of area to discussion, handling null or preventing null missing information. How do we do it? Well, fairly most obvious way is the not null constraint. It's kind of in the name, don't allow nulls. So how do we do it? I'm sure you're all familiar with this. We can just add not null after the column name when you're defining it. Now, what a lot of people don't know is you can also name not null constraints, and we can put that name here. We can put constraint and actually name your not null constraint. I must admit, it's very rare I see people actually do it. It's probably less of an issue than for other constraints, but if you want to be, fully complete, you can name not null constraints too. So we can use not null constraints to prevent nulls, but we can do it in another way as well. We can also use check constraints, right? Check constraints just evaluate deterministic expressions. So rather than not null constraint on the column, we could also define check constraints. Check that the column is not null, all right? So we can use that, do it via a check constraint. And like I say, check constraints can be other expressions as well. So we could do something like, check that the percent correct is something between 0 and 100. So people can't score more than 100 and can't get negative scores and things like that. So this brings another kind of interesting question. It's like, well, we've got not nulls and we've got check constraints, and they both can do the same thing. Again, why would we prefer not nulls? Why don't we just use check constraints and the extra flexibility it gives as well? So let's do another demo. So let's just empty the table out, and I'll add the not null check constraint. Do that and give it a name. Now I'm going to try, notice, although you can name not null constraints, you can't do it with the add constraint clause like this, like you would do with every other type of constraint. This will not work. If you want to name a not null constraint, you do it by modifying the column, which is perhaps slightly counterintuitive, but that's the way it works, right? So we can do that, we'll name that. And then we can look at our constraints, and at first glance, they look the same, right? They're both actually listed as C, check constraints, and they both have the same condition, basically speaking. So what gives? What's the difference here? Well, first up, when a check constraint fails, so we're trying to put nulls in these, you get the generic check constraint violated error, right? To know what condition has failed, you actually need to check it and look it up, or hard code it in your app or something like that. We don't know just by looking at this on its own that it's failed because this value is null, right? We need to do some lookups on that. Whereas not null constraints have a very specific error associated with them, 1400. So your error handling is a bit easier. We know it's failed because we're trying to stick null in here, whereas we know this has failed because there's a check constraint problem, but what exactly is that check constraint? We need to look and find out. Okay. The other thing is not null constraints give better information in the data dictionary. Normally, this nullable column and the tab columns things. So we can see student ID doesn't allow nulls, but even though we got the check constraint for course ID, the database says it does allow nulls. It's like, that's not right, right? So we get data dictionary information by using not null constraints. Finally, the optimizer actually has a little bit of better information as well. Okay, see someone, how does constraints affect querying? So this is an impossible condition, right? Can be no rows where student ID is null. And because we've got the not null constraint, the database knows this. So notice there's a filter operation above the table access. It only tries doing this when this is true, null is not null, that's always false, so it never accesses the table. The database knows this is impossible. But with our check constraint, sorry, I didn't do that, notice the conditions are underneath the table. It reads all the rows and then applies them. So if you write a query with impossible criteria for is nulls, the database picks that up with a not null constraints, but not for check constraints. So another reason why you might prefer it. I mean, in theory, you shouldn't need to write this, but obviously in practice, people do silly things potentially and so on, okay? So there's several reasons we might prefer not null. But let's go back to that multi-column foreign key. So first, let's just make all the columns optional. So we had 2 columns that foreign key. Let's say we want to make it the foreign key optional. So either all the columns are null or all the columns, both of the columns are not null. So as a group, they are null or not null. How do we do that? Well, you have to use a check constraint. You cannot do that with not nulls because they are always at the individual column level, right? So let's do that. We'll add that. And now we can set both of them or none of them, and we now prevent those impossible values. So either they're both set or they're not set. We cannot have these partial problems and don't have to worry about this dangling orphan values as well. So if you've got multi-column foreign keys that are optional, either make them all mandatory or use this check constraint like this. All right, let's go on check constraints. As I said, we can do other criteria, check the values between 0 and 100, and that stops all possible values, right? So we've got a negative value, big positive value, and null. But if you paid attention there, the null actually goes in. So that's because check constraints only reject rows where the condition is false, right? Null compared to anything is null between 0 and 100. Well, it's not true, but it's not false either. It's unknown. It only rejects false rows. So it fails the law of the excluded middle. The true and the not true, we return no rows, but that row is indeed in that table. So be careful with check constraints on nullable columns as well, right? It'll only get rejected if the condition is false. We can have these kind of disappearing values eventually. And just further, although the database couldn't use the check constraint for the is null condition, it can use it in general. So we said that no negative values are possible. So notice we've got this filter. We know this query can return no rows. The optimizer knows it too. So it can in general use check constraints. It's just the is null one that it doesn't find. Okay. So just to recap on that, not nulls, right? As I said, most people don't realize, but you can actually name not null constraints. You have to do it when modifying the column if it's adding it as new. And secondly, it has its own constraint, which is different to check constraints, which is always raised, the 2290. Check constraints, should be any deterministic expression here, and they only reject rows where the condition is false. Can lead to surprising results when nulls are possible. Finally, if you want a multi-column not null constraint, you have to use a check constraint. However, I would say if you've got a lot of columns as a group, which you want to say as a group are either null or not null, you should probably split those and put them into a separate table and put not null constraints on those. You probably shouldn't use that check constraint trick. You should probably put them in a separate, split it out into a separate table. Okay. Again, it's a bit more of a conversation for another day. All right, let's move on. And the question Brian was asking is like, if the duplicates already exist, can you add the constraint? So let's look at that. What do we want to do if we want to add constraints and there's already junk in the table, right? How can we do this, right? So let's say we'll keep it for our check constraint. We're going to try to add it, and there are negative or positive values in the table. So the whole thing falls over. There's invalid data, which doesn't conform to the constraint. It fails. So how can we do this? How can we add the constraint? Well, there is this NOVALIDATE clause, and what that does is it doesn't check existing rows. So we add the constraint and only new changes from that point on. So any inserts or updates from that point on must obey the constraint, but existing data might not. It might violate the constraint. So at this point, some people might go, well, why? What's the point in that, right? Why bother adding a constraint to a table if you're not going to validate the existing data, right? Well, so, you know, surely you just want to make sure everything conforms. Well, I can think of three good reasons why you might want to do this. If you've got more, please share. I'd love to hear them. But I can think of 3 good reasons you might want to do this. First up, maybe your data is just a complete mess, right? You've started working on a new project and there's no constraints. There's just nulls everywhere, stuff that shouldn't be possible, duplicates and so on. Sorting all the existing data out is a massive project in its own right. And it's a project that is never going to get prioritized. So it never actually happens. By creating the constraints NOVALIDATED, you stop the problem getting worse, right? You stop people adding new data which violates the constraint and give you time and let you clear that stuff up at your leisure without having to worry about things getting worse. So, you know, if you're in this situation, it's not great, but at least you can do something. The other thing is, it might be a new business rule. Maybe it's a business rule that's changed and it doesn't apply to existing data, or it's something you cannot apply to existing data easily. Let's say there's new regulation that comes in and says, from the 1st of January, you have got to capture the social security number for all your customers, right? And you've never been capturing this before, so you add the column to the table and all the values are null. And you can't populate them either, right? Or at least not by default. You know, you can't just make up social security numbers. You need to actually ask your customers and tell you what they are. So you want to add the constraint. So from the 1st of January, you know everyone from that point on is providing it. And again, we can sort out, maybe it doesn't apply to existing data and you can just move on, or maybe you can sort it out later. So it's worth bearing in mind, you might have constraints which only actually apply to a subset of your data, and that's okay. There might be scenarios where you might need or want to do that. The other one is kind of a practical issue, and that is when it comes to actually adding the constraint to the table. So adding a validated constraint is a blocking operation. So if you think about it, we want to check that all the percentage correct columns are all values between 0 and 100. The database has to read all the rows in the table and briefly take a lockout in the table to make sure that data is consistent and nobody has changed it in that time, right? So that is a blocking operation. To add a NOVALIDATED constraint is an online operation. So we might add it NOVALIDATED so we can do it while the application is running and then validate it afterwards, which is also an online operation. So we don't need to take an outage to actually add our constraint. So there's 3 reasons why you might want to do that. So let's look at these in action. Okay, so what I'll do, I'll recreate that student course results table and put some junk in there. So we've got duplicate rows and we've got percentages which are just all over the place, right? Well outside 0 and 100. So first up, we want to try and add our constraint here. There are values outside it, so it will fail. Okay. So at this point, I'm just going to, in a second session, I'll just pop this out. So I'm going to insert a row. So we've got that row. I've inserted that row. Because this is a blocking operation, the database can't take the lockout on the table, and we'll get the resource busy error. So we cannot do this while we've got that uncommitted transaction. We add the NOVALIDATE clause. You'll see it's stuck here waiting. In some ways, it can be a bit confusing. It's a non-blocking operation, but it is blocked by the insert. But the point is we can do this online. If I now commit this insert on this second session, you watch for that, you'll notice commit, and there the constraint is now added. And if I try and run this again, we get the check constraint error because that's been placed in there. Okay, so we've added our NOVALIDATED constraint and we cannot add more junk to the table. So let's just put that in. No more junk can go in. So let's clean up the data. In order to validate it, we need to clean up the data. So let's do that. Let's just set everyone's existing results to 0, validate it, and now we know all the data is correct, right? Everything conforms to that constraint. Just talk about, we want to make no validated, not null constraints. We can do that with no validate and modify and validate those. And let's try and create our no validated primary key. Create that, and well, that's interesting, isn't it? It didn't work. I added the no validate clause, but the database says it can't validate it. And it's like, well, I told you not to validate it. What gives? Why are you trying to do that? What's the problem here? Well, remember I said primary keys by default will try and create a unique constraint. The error is actually coming, a unique index, I should say. The error is actually coming from that unique index, not from the constraint, right? So even though we've created a no validate primary key, it's the unique index it creates that is throwing this problem, or tries to create, throws this problem. So how can we get around that? Well, remember that using index clause I was talking about earlier, way back at the start, you know, back in the good old days. We can use that using index. We can specify an existing index, or we can put an actual create index statement in there. And notice I'm creating a non-unique index there, and it's no validated. So we'll create that, and we've added that. So now we have prevented duplicates being stored in the table. So we can 5 goes in, but we cannot insert the second row. So once we've got that one in, we've got the new unique constraint in. If we want to validate it, let's just remove the duplicates, and we can now validate the constraint. Okay. There's one quick thing I want to show you before we finish up. If there's any questions, then let me know. Oh, I see there's a comment. Warning, the no validated constraint will still be applied on update statements of old customers with no social security number. Yeah, that's a good point. They say once you've added the constraint, even though it's no validated, it still will apply to changes to the table, right? So if it has a cutoff date, let's say you allow nulls before a certain date, you would actually have to do a check constraint, value is not null, and then like an insert date on the column, right? So there's a good point. Yeah, thanks for pointing that out. So you do need to think carefully if you do have like partial constraints or constraints on subsets of your data. All right then. This is a question that someone was asking before. If we do a create table as select, so let's do a create table as select. They're asking about what constraints are copied. So why did I have that? I'm not sure why I put that there. Anyway, if we look at the constraints there, we notice our table we've created, the only constraint that's copied is the not null constraint. The primary key and the check constraint are not copied. So only not null constraints are copied. And the question is why? Why is this? Well, again, it's partly the answer is that's because the people who made this, that's how they decided to do it. But I think, well, why did they decide to do it that way? Okay, come on, Chris. I think there's a few good reasons for this. So first up, it's worth remembering this can be any query, right? In general, actually, it probably would be, if you're doing a lot of create table as select as just straightforward select the original table, I think you're doing something a bit fishy. Normally, this would be some kind of query, maybe a join, maybe an expression changing the values, where you can't necessarily apply the constraints from the table to the new table, from the old table to the new. You might have data that violates the constraints, right? So in general, you can't just copy the constraints as is, because it will fail. It'll cause the create table to fail. But also, secondly, there will be situations where you do not want the constraints, right? Maybe you're creating this table and you don't want the constraints on it. You'd have to have a way of unspecifying them, which kind of doesn't really make sense. It probably makes more sense to be active and specify what you want. And so you can do this in the column list. So we've got create table as select, and notice I've got a bunch of constraints that now I'm adding here, not null, primary key, and so on. So I create that table and it adds the constraints. So you're using create table as select, and you want anything other than a not null constraint, you define it yourself in the column list like this. Or you can, of course, you can add them after as well. All right. I'm aware we're kind of slightly past the hour, so I will recap quickly. And if you've still got more questions, I'm happy to hang around a bit if you want to discuss a bit more. Okay, so let me recap. So first up, why do we create constraints? To stop me having errors where I misspell error and things like that. Okay, key things are we prevent duplicates with primary keys and unique constraints. Foreign keys prevent orphaned values. Not nulls prevent nulls. That does what it says on the tin. And check constraints prevent other types of impossible values according to your business rules. As I say, you can name these. As I say, it's a very, very good idea to name your constraints. It makes the errors easier to pass, makes it easier to query the data dictionary and so on. And you just do that. You have constraint and give it the name. If you do not give them the name, the system will generate them for you, which makes it a little bit tricky to know what's going on if you're looking at error messages or the data dictionary and you just see a bunch of sys something or the other. You have to do further investigation. Finally, we talked about this briefly, and it is a bit more of a niche thing, but it does come up in some cases. If you've got the constraints, validated constraints on the table, the optimizer can recognize this and use it to factor out impossible conditions, which can lead to better performing queries. So you're giving the optimizer more information about what's possible to make things better. The question I'm sure everyone always has is, where can I get the scripts? So I've loaded these all into Live SQL. So if you want to check those out, we've got the Live SQL link there. It's on the Ask Tom Office Hours page itself. So if you want to go check there and take a look. So with that said, all that's left to say is I really hope you enjoyed this. More importantly, I hope you learned something. Today's Trove Tuesday, Pancake Day. So for those of you who celebrate such things, I hope you have enjoyed eating your pancakes, and I hope to see you next time. All right, goodbye.